Okay, so yeah, someone messaged saying that next week the MTech students are having exam. Yeah, that is true. I am aware of it. So which is why you do your preparations this week. Zeroth review is not very extensive. It's just to make sure that you are getting started and that you are on the right track, and then you have divided your work fairly well. So it's not a very intensive presentation. So I am aware that the third week of November you are having exams, but you can do it this week, and I don't think it's going to be a very heavy one. Plus you're kind of running out of time, so that's another thing. Okay. All right. So let's get started. So in the last few classes, we have been looking at different versions of the common source amplifier. We saw a common source amplifier with a resistive load, right? And we looked at its signal swing limits, right? We looked at its gain, the bandwidth, the noise performance, and what is the min swing and the max swing, and where does the output DC point get to? Okay, the DC part, the AC part, we have looked at it. Another thing that we looked at was basically to use a diode connected MOSFET as your load, right? This was another circuit that we looked at. Okay, and this was using a diode connected N MOSFET. We also saw the same circuit with a diode connected P MOSFET, and for all these things we looked at the gain performance, the bandwidth, we looked at the output impedance. Of course, the input impedance is capacitive, and we looked at the signal swing limits, the DC performance, the transfer curve, all these things, right? And then we moved on to what is called as the common source with the current source load, right? And in fact, what happens is this is one of the most commonly used topologies for common source. And today we will look at a few more variants as well before moving into common gate amplifier. All right. Okay. So one extension that you can see here is, so in all these cases, the thing is all the transistors have to be in saturation region. So this is another tip when you do your project as well, not only your project but also your assignment. By the way, I am in the process of preparing your next assignment, which is kind of half done from my side. By this evening, I will upload it, so you can go through it. It will also have some simulation exercises. The simulation exercises, the MTech students, I will give some extra simulation exercises, so that will count towards your lab. Okay. Of course, the simulation exercises which are common to all the students will be, all of you will have to do. There will be a separate set of simulations which are optional for the other students, but is mandatory for the MTech students because it counts towards your VLSI lab. Okay. Now, so please do that also seriously. The way I am planning is that by the time you start with your project, you would have already designed all these building blocks. So the basics you will already be thorough, so that you can jump right into your project. So that's the idea. Okay. Now so here the thing is, all what we have seen here is that all the transistors are in saturation. In fact, the tip to get your circuits to work, okay, the first tip is to just biasing it correctly. Okay. Although you have all the other criteria, this goes for op amps and buffers and filters and whatever you do, okay, whatever analog circuit you do, in most cases, except for very few cases where the transistor is expected to operate as a switch or in the triode region, the other transistors by and large are expected to be in the saturation region. So the way in which analog design typically works is basically you have a set of specifications. Okay. Now the specifications can be like gain, bandwidth, or the UGB, or it can be the signal swing limits. It can also be noise, definitely, and the specifications can also be in terms of linearity. when I say linearity in terms of HD2, HD3 and so on, harmonic distortion. And the specifications can also be in terms of input bias and so on. Now, all these things, when you are doing a design, what I'm telling you is common for all your simulation assignments as well as for your project. Okay. So what you need to do is you need to translate these specifications into certain other second order parameters, okay, or small signal parameters. Okay. Now, one important spec is also power. Okay. Many times you end up with a power budget. That is, your op amp which you are designing should not consume more than 1 milliwatt. So which means that all the currents which are drawing in your circuits should be less than, the power should be less than 1 milliwatt. So if you are using, let's say, a 1 volt supply, you have to draw less than 1 milliamp. Okay. Or if you are using a 1.2 volt supply, it should be less than something like a 0.8 milliamp or something like that. Okay. So power budget is also a very important thing. So all these things will come down to what you have. Of course, VDD is kind of given. You don't have any control over it. Okay. So it comes to either the drain current or GM. Okay. And of course, see, the load capacitance will also be typically given to you. So from all the set of specifications, you end up deriving these other parameters, R out, okay, and things like that. Okay, GM, R out, ID, and of course the V in DC, the expected V out DC. Okay. Now from this, what you need to do is you basically need to first do DC biasing. Okay. The moment you do proper DC biasing and all your transistors are in saturation, you've kind of crossed, 3/4 of your problem. Okay. So from your set of specifications, you kind of derive the current. For example, let's say you're designing this common source amplifier. Okay. And I'm giving you, let's say, a power budget or input. You will not get all the budgets all the time. You will get some combination, right? Given a certain combination, you have to derive what is the drain current that I'm going to design for, what is the GM that my transistor is going to have, what is the R out that I'm looking for. Okay, so from there you go into actual DC biasing, and then you go for your other verifying and design modifications to meet spec. Okay, all right. So don't start with the gain curve. A lot of students make that mistake. Okay, first they go and start running an AC simulation to see what is their low frequency gain or what is their bandwidth. That is not at all the first simulation that you do. Okay, more than 3/4 of your battle is won with DC. All right, just by doing only DC simulation, more than 75% of your design work will get done. Okay, and after that you go look at the AC simulation or the transient simulation, and then you come back and see which parameter needs tweaking, and then you have a few iterations and you get the job done. Now from going here to here, you have the equations, small signal model, whatever we are doing right now in class, right? So you do that. Now from here to the other things, you have to use the plots. Okay, don't use mu n Cox, mu p Cox, VTH. Do not use these parameters. All right, you have to use the plots. What do I mean by the plots? That was your previous assignment where you had to generate ID versus VGS plot, GM versus VGS plot, right? So if you are looking for a certain GM value and you're looking at a certain VGS value, you just need to scale the transistor W/L ratio to get the current and GM that you need. That's it. Okay. So you use these reference plots, okay, and R0 versus VDS. Okay. So these are the plots that you kind of use as your handy tool, or GM over ID by VGS. That's a very important plot. Okay. So you use these plots to generate the WL biases, etc. All right. don't use the square law equation, don't use the device equations, because they will not be correct. Okay, especially 65 nanometer, and those you'll get completely thrown off. All right. So, and then of course you go and do your verification and so on. Okay, so keep this in mind. Most of the things is, or your transistors should be in saturation. Okay, all right, fine. So that's a little tip about a design. I'm thinking maybe in the next class I will just show you an example design so that you kind of get the hang of it. All right. So today we will just cover a few other topologies. Okay. Now one other topology which I think you also can kind of guess is like this common source amplifier with a resistive load can also be implemented as what? You can use a transistor which is in triode region. Okay. So here what happens is M2 is in triode region. So what happens when your transistor is in triode region? I mean, it can be an NMOS or it can also be a PMOS. Okay, that's fine. All right. Now what happens when you have a triode region? You have an on resistance which is given by approximately 1 by mu n C of W over L, VGS minus VTH. Okay. Now all you can get from this is basically you can say that the on resistance of this triode thing is inversely proportional to your W over L ratio. It's also inversely proportional to your VGS minus VTH. Okay. Or in other words, it is inversely proportional to your gate to source voltage. Okay. So if you give larger gate to source voltage, you basically get lesser resistance. Okay. And if you have a wider dimension, or if you have a higher W by L ratio, you get a lower on resistance. Okay. So this is of course valid only when the region where M2 is in triode region. So that is what is going to set your swing limits. Your Vout min, right? If you take a PMOS device, now your Vout min should be such that M2 stays in triode and M1 stays in saturation. Okay. So this is the key thing. All right. So as long as this is happening, you have a you can have a device like this. So rarely, in some cases, you use the MOSFET in the triode region and use it as a variable resistor or a voltage controlled resistor. Why is it a voltage controlled resistor? Because of this particular dependence, right? If you change the VGS value, if you change the gate to source voltage, then you get a different value of resistance. So if you end up in a scenario where you need a voltage controlled resistor, okay, given that the biases and the DC voltages are such that you do not have this stays in the triode region, you can use the MOSFET as a voltage controlled resistor. Okay. Now the concepts that you are learning in all these small circuits will all build up when you look at a bigger circuit. Okay. So these are same concept. If you are able to just take a big circuit, divide them, identify them as different blocks, it is very easy for you to analyze any complex circuit. Okay. All right. That's why we are spending a lot of time in looking at these basic fundamental blocks, because if you get this right, the rest of the course becomes very easy. Okay. If you are not sure about this, if you are kind of very unsteady in this, then the rest of the course will make no sense to you. It will be all Greek and Latin. Okay. So I would encourage you to read chapters 3, 5 and 7, or 3, 6 and 7 in Razavi's book, based on what I have done. Okay. As I mentioned, like due to the limited time, I cannot go through each and everything, but I'm trying to cover as much as possible. Please read the textbook also. All right. And take the assignments that I give you seriously. Try to work it out on your own. Don't do copy work. Okay. And that's the way you learn the subject. All right. And so even in quiz 2, I will ask things which are kind of beyond what you have in the assignments and so on, where you need to apply your the concepts that you learn here, maybe be able to implement your, draw a small signal circuit, do your small signal analysis and get the answers. Okay. All right. Now we come to another important variant of common source, which is common source with an active load.
Excuse me, sir.
Yeah.
Sir, in the previous slide,
Yeah.
sir, here if M2 is an NMOS,
Correct.
then in that case, sir, VGS will depend upon Vout.
Yes.
So, like Vout, in order to get some, let's say, some steady state or some DC value of Vout,
Mm-hmm.
we have to depend on Vout itself to bias M2. How do we do
Okay.
that?
Okay. Okay. Good question. Good question. Let me clarify that point. Okay. Yeah. So let's say we have some VB. All right. VN. This is a very good question because if you understand the underlying concept, these are some of the very fundamental concepts. Okay. Now, what sets the VG? So here, there are two transistors in the same path. All right. So ID1 is equal to ID2. All right. So when you are designing, you have to make sure that you design both the biases as well as the W by L ratios such that both of them are able to handle the same amount of current. Okay, you want both of them to be in saturation. Okay, now the way it works is this. All right, let me just throw in some numbers. Okay, so that we kind of have a better understanding. Okay, let's say for V in for M1 transistor, V in DC, okay, is let's say 0.4 volt. Okay, and let's say you have a certain WL ratio which supports let's say yeah, what is happening, 250 microamp of current. That is, you're looking at this plot. This is VGS, this is ID. Okay, for this W by L ratio, let's say you are somewhere here 0.4 volt and the current is 250 microamp. All right, so you are setting M1 to be such that this is, let's say this W by L ratio is, let's say 10. So let's say you have 60 nanometer, 600 nanometer as the width. Okay, and this DC voltage is set to be 0.4 volt. Okay, now let us say VDS sat 1 is let's say let's say 180 millivolt. All right, let's just say, so you do a DC simulation, you know that the VD sat is 180 millivolt, which means what? This V out has to be greater than 180 millivolt for this to work. All right. Now, what is actually setting the V out? Now, what is setting is, let's say the supply voltage is 1.2 volt, and now you have to design this M2 transistor. All right. Now, you have all the other parameters in under your control. Okay, let's say this is going to be 1 over GM. So let's say you want a certain VGS to be VGS2 to be, let us say 0.45 volt. All right, you got my point. You get this VGS from, let's say you have a gain thing of let's say you have a certain gain value, and it is given by GM1 divided by GM2 plus GMB2. Correct. This is the gain formula that we got. And let's say from this, you know ID value because you have set it. Let's say you have a power constraint, and from there you say I need a certain VGS value. How will you see this VGS value? Again, you go to the GM versus VGS plot, right? It will go something like this. Okay, so you say, okay, for this ID, okay, I am choosing my W by L ratio also to be a certain thing. Let's say this W by L ratio is given by a factor of 8. Okay, I'm just giving you some examples. Now, the way you would design it is, you will select, you have to design VB. Now VB is equal to what? VB is equal to this VGS2 plus Vout. Okay. All right. So now your Vout has to be at least 180 millivolt. Let's say you want to have your Vout at, let's say, 0.35 volt. Okay. Let's say that's where you want to fix it. You're fixing Vout to be 0.35 volt. So which means what? VB is equal to 0.35 plus 0.45, which is what? 0.8 volt. Okay. So now what happens? This transistor, let's say this is 8, and so you are having 60 nanometer, and then you have 8 into 4, 6 is what? 480 nanometer, and this is 0.8 volt. Okay. So now if you do this, your Vout will be nominally at around 0. What was it we wanted? 0.435. All right. So suppose, so the way it happens is, suppose you change the gate bias. All right. Instead of 0.8 volt, so till now you understood, right? How you will design this amplifier?
Yes, sir.
Yeah.
Yes, sir.
Okay. Now, suppose, okay, this is supposed to be in the triode region. Okay, I'm sorry. So you kind of, we are just assuming that, it is in the triode region, and then it is not GM1. I just got confused. So from R on, so from here you calculate the VGS. So which means that typically this VGS, let's say, is 0.55, and let's say this W by L ratio is 20. Okay. So then if it becomes 20, 60 into 2 is 1.2 micron. Okay, and this is going to be what? 0.35 plus, let's say, 0.55. This becomes 0.9. Okay, so this becomes 0.9 volt. Okay, all right. So till now you understood. Now suppose I am giving you a scenario. Okay, if VB is set to, let's say, 1 volt. Okay, that is, you have increased VB. You wanted 0.9, then you said Vout will be 0.35, and now you have increased your VB to 1 volt. Now what will happen? Now what will happen is this. Okay, as long as the current remains the same. Okay, if this becomes 1 volt, if the current is the same, now this will drop 0.55 here. Okay, and it will drop 0.45 here. You understood? So this transistor will take only the gate to source voltage that it needs to support that amount of current. Okay, in practice, when you simulate it, the other second order effects like, the body effect, and also channel length effect, first of all, channel length modulation effect. So all these other things will come into the picture, velocity, saturation, and things like that. Okay, so you will have a little difference. Okay, but to a first order, you can say that this transistor will take only the VGS that it needs to support the current that it needs. The current might slightly increase, okay, because this VDS is increasing. So because of channel length modulation effect, this current will slightly increase. But the rest of the current, the rest of the voltage will come across your M1 transistor. All right. Okay. So does it answer your question? So the VGS is kind of, instead of saying that the Vout is set current, I mean, instead of going that way, when you're designing the circuit, what happens is you set the bias voltage and design the transistor in such a way that it will take only a certain amount of VGS, and the rest it will push across your next transistor. All right. So this is how it works. Okay. So even in op amps, everything, this is the concept that happens. All right. Okay. So now let's go to this. Anyway, thanks for asking this question, because I wanted to clarify this point. Some of these things you will learn only when you start simulating, designing circuits, and you will see it in practice. Okay. So common source with active load. Now this might look like a very fancy term. All right. But I will draw the circuit, and many of you will know what I am basically drawing. What is the circuit?
Sir, inverter.
Exactly. It's a digital inverter. Okay. Now, a digital inverter has a voltage transfer characteristics like this, right? So, V in and V out. So, what happens when V in is 0, this is at VDD, and then when this is at VDD, V in is at VDD, V out is at 0. So, there is this in between region where there is this transition happening. Okay. So, the digital people use the inverter obviously as a, whether it works either in this region or in this region. Okay. As analog design engineers, you can make use of the this particular circuit in this particular region. Okay. So what happens is you see that there is a very steep slope here. All right. So basically what it means is there is a voltage gain happening in this region. So if you bias your transistor in this region, okay, where both the PMOS and the NMOS is on, and both PMOS and NMOS are in the saturation region, then you end up having a amplifier. Okay. So in many in quite a few cases, in fact, like especially with the deep submicron transistors and so on, people use this or some variant of this. Sometimes people just put a resistor in between to a large resistor in between to basically self bias this inverter. Okay. So if you put a very large R here, what happens is the AC current does not flow so much, but the DC voltage is maintained at half the VDD, or in half the VDD if the strength of NMOS and strength of PMOS is the same, or somewhere close to half your VDD in this transition region, such that the current of M1 is equal to current of M2. All right. So it will this is what is called as a self-biased inverter. Oops, what is this? Okay, so this with the resistor, it is called as a self-biased inverter, and in fact, this is used kind of fairly well in a lot of situations. Okay, so and especially where when you have these high-speed links. Example of high-speed links can be your DDR interface. Okay, your DDR RAM with your processor. You want your the data rate to be pretty high, right? So in such cases, when the signals are flowing at the receiver end, the signals are not very good square waves. Okay, they become more like some kind of sine waves. All right, because of the bandwidth limitation of your PCB channel between your DDR RAM and your processor. Okay, the same thing happens in network backplanes and so on. So that's a whole area of work that goes on. In fact, the MTech students will have a course next semester, mixed signal VLSI, where half the course we look at high-speed I/O interconnects. Okay, so in situations like this, under certain circumstances, you use circuits like this. In fact, people try to use this for even LNAs and so on. Okay, so all that apart, so this acts as an amplifier. All right. So now, without the resistor, can we draw the small signal equivalent circuit? So I would encourage you to draw it on your own. Okay, and I will just give you what I will do is, I think the best way to do it is to give this as an assignment. Okay, so please do it. Let me just give you a brief thing. Okay, you can, let's say this is your VDD, which is an AC ground. Okay, this transistor is in saturation, and this is nothing but GMVSG, as I mentioned in last class. For PMOS, you just switch the subscripts. That is enough. Okay, and this is R0. The body effect is not in the picture because both the transistors, the bulk and source are connected. Here you have GM1, this is GM2, VGS here, and you have, let's say, R0 to R01. All right, and this is your V in. This is grounded. Sorry, your V in is not connected here. Okay. V in is coming here. So VSG is given as this polarity and VGS is given as this polarity. So Vin is equal to VGS is equal to minus VSG. Okay, all right. So this is your V out. So you can write the rest of the analysis and you can find out. So I will give this as an exercise where you can find out what is the gain, what is the R out, okay, what is the bandwidth, okay, and what is the input referred noise. So I would encourage you to do it. Input referred noise, as I mentioned, so you have two transistors in saturation, two noise current sources will be there adding together at the output node, right? And so because both are uncorrelated, you can just add them together and then divide by the gain squared to get the input referred noise. Okay. So and also the output swing limits. So take it as an assignment and derive it. Okay. So what you would see is the final result will look something like this. You have GM1 plus GM2 into R01 parallel to R02. Okay. So R out is nothing but R01 parallel to R02. It is easy to see. And you will see that two transistors, see in the previous case, right, where you had a, in this particular case, this transistor was a current source. Okay. The GM of this transistor did not come into the picture. The signal is not going to the gate or the source of this transistor, right? This transistor is just at DC, it is going to give you a constant current. So only the bottom transistor's GM was in the picture. Whereas in the case of an inverter, what happens? The input signal is given to both the transistors, M1 and M2. And therefore, what happens? Both the transistors GM is involved. That is why you will see that GM1 and GM2 is there. So you can derive this. Okay. And of course, the output impedance is R01 plus R02. All right. Okay. So another variant that we can see here is basically common source with source degeneration. Okay. So what is you can take any common source here. Okay. So right now maybe I'll just maybe what I will do is I'll just put a current source here, ideal current source right now. Okay. You can derive it for all the other cases as well. Okay. Let me just use a resistor here. Okay. Now this is a common source with source degeneration. So I hope all of you are familiar with this concept of source degeneration. So basically this acts as a negative feedback loop. In what way does it act as a negative feedback loop? See, suppose let's say Vin, let's look at the DC first. Okay. So if Vin increases by a small amount, okay, I'm not talking about large jumps. Let's say Vin is increasing by a smaller amount. All right. Now what happens? Now the VGS of this transistor will increase because assuming that the source is at the same potential, your gate alone has been increased, right? So your VGS has increased. Now if the VGS of the transistor has increased, this will lead to what? ID to increase, correct? Because ID is highly dependent on the gate to source voltage, right? Now if ID increases, this leads to what? Sorry, this is not RD. Let me use the name RS. Okay. So if we call this as VS, which is the drop across the source resistor, now that your drain current has increased, okay, drain current being equal to your source current increases, and therefore VS is equal to ID times RS also increases, correct? Now because your VS has now increased, what happens? Now your VGS decreases, okay, which leads to ID coming back to the original value. Okay. So you see that this is a negative feedback loop. You started with a certain action, okay, and it came back to you, pushing you back to the same place. Got it? So you started with increasing your V in. Now this is the same for let's say even your AC signals and so on. Of course, the other non-idealities like channel length modulation effect, the body effect, and all these things will come into the picture. But if you look at DC, or if you look at even small signals, okay, there is this effect of a correction, some form of a correction which is happening. It is not going to be perfect correction, because of course you can use the tools of negative feedback that we used here. You can say that, you know, the input to output is a voltage to current conversion, and the feedback is done by, you know, current to voltage conversion through this resistor. You can, you know, put this as a feedback factor, and then you can look at the closed loop response. Basically what you will see is, see the forward, you can kind of understand this as, okay, if you look at only the current, if you look at the current, okay, so you have a certain action, okay, coming in, you have a GM which is producing a certain ID, right, ID, and you have RS as the feedback factor, okay, which is kind of, you know, bringing it back to, you know, RS times ID is also bringing it to, it's in the voltage, so this is V in, and then you have I out, and this is the feedback loop, okay. So we know that if you have a feedback loop, everything gets scaled by the loop gain, right. Now what is the loop gain here? It is GMRS, or rather it is scaled by 1 plus the loop gain, which is nothing but 1 plus GM times RS, okay. So now if you see, everything that you see here will get scaled by this factor of 1 plus GM RS, okay. Let's try to do that. So let's try to draw the small signal equivalent circuit. So first I gave you this circuit, and I kind of proved it to you that it is a negative feedback system because of the source resistor, so that if you cause some disturbance at the input, okay, the current comes back to the same value, okay. So if you look at the gain, you just put GMRD here, then, you know, this current going through the gain, through RD will give you the gain, okay. So everything gets scaled by this feedback or loop gain factor, okay. So now let us kind of see whether this is really the case by doing a small signal analysis. All right. So how do we do the small signal analysis? We have RD here, we have RS here, we have V in here. So first let's start with the device, right. So we have GM times VGS, we have R0, okay, and so here this is your source, this is your gate, this is your drain, okay. So at the source you have a resistor RS going to ground, and then at your drain you have RD going to ground, correct, because this RD is going to ground, and this is your V out, alright. And V in is defined as what? V in is defined as the voltage between the gate and the ground. So this is your V in, okay, and your VGS is what? Between the gate and the source, okay. So now you can analyze this by saying that V in is not VGS is nothing but V in minus Vf. And what is Vs? Vs is nothing but the current Is into Rs. So what is Is here? It is GM VGS plus V out minus Vs divided by R0, okay. So you can, in this case, you can assume that R0 is much greater than RD, and that also simplifies our, you know, let me just put it in a different color just to show that, you know, we are kind of neglecting the effect of R0. So neglecting R0, so what happens? Is is nothing but GM times VGS. So you substitute the whole thing, VGS becomes V in minus Is times, which is Gm VGS times Rs, correct? So what does this become? VGS into 1 plus Gm Rs is equal to Vin. Okay. So this is the equation. Now what is V out? V out is nothing but minus Gm VGS into Rd. Now what is VGS? You substitute for VGS, it becomes minus Gm Vin times, right? Vin divided by 1 plus Gm Rs. So basically it leads to a voltage gain of minus Gm Rd divided by 1 plus Gm Rs. Okay. So this negative feedback system, alright, this negative feedback system, what it is doing is basically, we are talking about the effect on the current, basically, only the current we are looking at. So if you look at it, GMRD minus GMRD is the common source without source degeneration, correct? So that is scaled by a factor of 1 plus Gm Rs, alright. Now you can also derive what is your R out here, okay, and again I would like to leave this as an exercise. You can put the connect a test voltage source and basically see what is happening. You set V into 0, and you have to be careful because VGS does not go to 0 because Vin is set to 0. VGS just becomes minus of Vs, and so you will see that it is more like R out is nothing but Rd in parallel with, okay, it is like the cascode's output impedance, okay. Or in the case of a cascode, you remember when we did current sources, we said we have M2 and M1, right? And we said the output impedance is nothing but R01 plus R02 plus GM2 R02 R01. In other words, you can think of it as, let's say this is M2 transistor with R01 at the bottom, right? And what you see here is this impedance plus Gm, the gain of this into R01. So here also you can write it as Rs plus R02, or in this case there is only one R0 plus Gm R0 into Rs. Okay, so this becomes your R out. So for all practical purposes, it just becomes Rd. Okay. So this is the thing. Then you can look at the, once you know R out, you can write your bandwidth equations and other things. All right. So source degenerated common source will give you lesser gain. Okay, and you will also see that if you look at the you will have lesser gain at this place, but there is a flip side to it. Okay, you have lower gain, but what happens is, as we saw, I think in the context of the negative feedback loop, one of the assignment problems that I had given is in the presence of noise or distortion, a negative feedback loop will suppress the effect of nonlinearity or the whatever is getting added in the loop, right? That was one of the assignment problems. Okay, so here also you would see that if you model this as some kind of a noise which is added, not noise, distortion which is added because of this transistor. See, we know that this transistor is a nonlinear device. Okay, it is linear only over a certain very small range of the small signal range, correct? Now what you will see is you will have better linearity here. Okay, negative feedback loop improves your linearity. Okay, so in fact what happens is, especially in certain critical applications where non-linearity is of a concern, okay, and you are not able to meet the linearity specification. Let's say you have a very tight HD2 spec or HD3 spec, okay, and you are not able to meet it, people resort to degeneration to get that to work. Okay, so source degeneration is done mainly for this reason, okay, to improve the linearity. Okay, all right. So with this we are completing our discussion on common source amplifiers. Maybe next class I'll just take common gate and common drain. All right. And we will move on to differential pairs, and from there we will move on to op amps. Okay. All right. So any doubts, any questions so far? Okay. All right. So what I mentioned at the beginning of the class is that those who have not yet formed their groups, so please do form your groups and let me know by today. And please pick your topics and let me know by Tuesday or Wednesday max. Next week we will have a zeroth review. Pick your topic, just go through some material in the textbook, see how you are planning to divide the work among yourselves. You can just check some papers online and also the textbook, and a combination of the two should be good enough for you to do the project. Okay. All right. So with this we'll conclude today's class. Thanks everyone and have a nice day. Yeah.
Sir,
Yeah.
for the quiz, till what portion should we expect?
Yeah, all what I'm covered after the first quiz will be there in the exam. Okay.
Okay, sir.
Yeah.
Yes.
Okay. So thanks everyone. Have a nice day.